From the moment humankind first looked up and saw lightning crackle across the sky, we've been captivated and terrified by the raw power of extreme weather. Tornadoes that can fling cars like toys. Blizzards that shut down entire cities. Droughts that reshape landscapes and livelihoods. These aren't just atmospheric oddities, they are nature's most dramatic expressions, and they demand our attention. But beyond the drama lies a complex science that meteorologists are only just beginning to fully understand. Extreme weather isn't merely about chaos, it's a phenomenon deeply intertwined with climate systems, geography, and even human behavior. Whether it's the perfect storm born of warm ocean waters or a heatwave intensified by urban infrastructure, the science behind these events is intricate and often surprising. And as our climate changes, so does the behavior of these events, making it more important than ever to study how and why they happen. Scientists are not just trying to predict them, they are racing against time to understand their new patterns. In this video, we'll dive deep into the art and science of extreme weather. We'll unravel the mechanics behind the most awe-inspiring natural events on Earth, from hurricanes and hailstorms to megafires and atmospheric rivers. Each segment explores the science, the danger, and the stunning beauty of these atmospheric outbursts, all backed by real-world research and verified data. So grab your raincoat, or maybe a fireproof shelter, because we're about to enter the storm. Supercells and tornadoes. Twisters unleashed supercells are the grandmasters of violent weather, responsible for producing the most intense and long-lived tornadoes. These rotating thunderstorms form when warm, moist air meets cold, dry air under the right wind shear conditions. Inside these storms, a rotating updraft called a mesocyclone can drop a funnel cloud, which may develop into a tornado. Not every supercell spawns a tornado, but every significant tornado starts with a supercell. Tornadoes can vary drastically in size and strength. The Enhanced Fujita Scale, or EF scale, classifies them from EF0 to EF5 based on the damage they cause. While most tornadoes are short-lived and relatively weak, the rare EF5 events can exceed 200 mph winds and carve paths of destruction miles wide. These twisters are terrifyingly beautiful, often appearing as elegant ropes or monstrous wedges on the horizon. Research into tornado formation has made significant strides thanks to tools like Doppler radar and storm-chasing teams. These scientists brave the front lines of nature's fury to deploy sensors and study the anatomy of the storm. Yet, despite all technological advancements, tornado prediction remains notoriously difficult. Warning times are often limited to mere minutes, leaving little time for evacuation in the most dangerous cases. The U.S. Midwest and South, often dubbed Tornado Alley and Dixie Alley, respectively, are prime hotspots. However, as climate patterns shift, tornadoes are being reported more frequently in regions outside their traditional zones. Understanding these trends is crucial not just for public safety but also for urban planning and infrastructure resilience. Hurricanes. Giants of the ocean. Hurricanes, also known as cyclones or typhoons depending on the region, are massive storms that can span hundreds of miles and last for days. They feed off warm ocean water, typically above 26.5 degrees Celsius, and gain strength as they move across the sea. The core of the hurricane, known as the eye, is an eerie zone of calm surrounded by the eye wall, where the storm's most powerful winds and rain rage. The Saffir-Simpson hurricane wind scale ranks hurricanes from Category 1 to 5, with Category 5 storms bringing catastrophic damage through winds exceeding 157 mph. These storms are not only wind events, they also cause deadly storm surges, which are sudden rises in sea level that can flood coastal areas. In fact, storm surge is often the most lethal aspect of a hurricane. Climate scientists have found that while the total number of hurricanes may not be increasing dramatically, their intensity and rainfall are. Warmer sea surface temperatures and more humid atmospheres contribute to the formation of stronger, slower-moving hurricanes. This slow movement increases the duration of heavy rainfall over one area, compounding the potential for flooding. Recent storms like Hurricane Harvey, 2017, and Hurricane Ian, 2022, have shown how urban development in coastal zones compounds the risk. Cities like Houston and Miami face increasing danger from these megastorms. As a result, there's growing momentum to update infrastructure, enforce stricter building codes, and improve early warning systems to better prepare for future landfalls. Flash floods. When water strikes fast, flash floods are sudden and intense flood events, often triggered by heavy rainfall over a short period, especially in urban or mountainous regions. They are among the most dangerous forms of flooding because they can develop in less than 6 hours after rainfall begins. When storms dump vast amounts of water on dry, compacted soil or on impervious urban surfaces like asphalt and concrete, the water cannot absorb, it runs off rapidly, overwhelming drainage systems and riverbanks. One of the major risks of flash floods lies in their speed and unpredictability. Unlike river floods that may take days to reach peak levels, flash floods can turn a dry street into a raging torrent in minutes. This sudden onset is often deadly for people caught in vehicles or low-lying areas, especially in regions with limited emergency warning systems. Even a few inches of fast-moving water can knock a person off their feet or sweep away a car. Climate change is playing a role in exacerbating flash flood risks. Warmer air holds more moisture, increasing the likelihood of short-duration, high-intensity rainfall events. Urban sprawl also adds to the problem, as expanding development creates more surfaces that resist absorption. Cities like New York, Berlin, and Mumbai have all experienced flash floods with deadly consequences, exposing the vulnerability of urban infrastructure. To combat this, many cities are investing in green infrastructure, like rain gardens, permeable pavement, and expanded wetlands to help absorb runoff. Smart drainage systems, early warning phone alerts, and predictive models based on real-time radar and satellite data are also being used to give communities a fighting chance. But ultimately, preparedness and public education are key to reducing flash flood fatalities. Lightning. The shocking force of nature. Lightning is one of nature's most dramatic and dangerous spectacles. It forms when collisions between ice particles within thunderclouds generate electrical charges. Positive charges build at the top of the cloud and on the ground, while negative charges concentrate in the cloud's lower regions. When the electrical difference becomes too great, a bolt of lightning is discharged, often striking the ground, illuminating the sky, and producing thunder. Each year, lightning strikes Earth over 1 billion times. A single bolt can contain up to 1 billion volts of electricity and reach temperatures of 30,000 Kelvin, hotter than the surface of the sun. While most lightning strikes occur within clouds, cloud-to-ground strikes pose serious risks to life and property. In the US alone, lightning causes dozens of fatalities annually and millions of dollars in damage to buildings, forests, and power infrastructure. There are various types of lightning, including sheet lightning, which lights up the sky without a visible bolt, forked lightning, which branches jaggedly, and even ball lightning, a rare and poorly understood phenomenon involving glowing, floating spheres of energy. Recent studies have also captured sprites and blue jets, electrical discharges that leap upward from storm clouds into the upper atmosphere. Lightning detection networks and real-time strike mapping have significantly improved forecasting and safety measures. Outdoor warning systems, mobile alerts, and public awareness campaigns help reduce lightning-related injuries. Still, the advice remains timeless and simple: when thunder roars, go indoors. Avoid open fields, tall trees, and metal objects during storms. Lightning doesn't play favorites. Blizzards and ice storms. The frozen threats. Blizzards are powerful winter storms defined by strong sustained winds, low temperatures, and heavy snowfall, reducing visibility to near zero. What makes a snowstorm a blizzard isn't just the snow, it's the wind. According to the National Weather Service, winds must exceed 35 miles per hour, and visibility must remain below a quarter mile for at least 3 hours to qualify as a blizzard. These conditions can immobilize entire cities and endanger lives through hypothermia and accidents. Ice storms, though less dramatic in appearance, can be even more destructive. They occur when rain falls through a layer of freezing air near the ground, turning into ice on contact with cold surfaces. This results in a thick glaze on roads, power lines, and trees, creating dangerous conditions and widespread outages. Just half an inch of ice can add 500 pounds of weight to power lines per span, often snapping them and plunging areas into darkness for days. Both types of storms are becoming more erratic due to shifts in the polar vortex and jet stream behavior, attributed by many scientists to climate change. Cold air that was once trapped in the Arctic is increasingly spilling southward into North America and Europe, delivering unusual deep freezes to regions unaccustomed to such events. The Texas freeze of 2021 is a stark example of the deadly consequences of infrastructure unprepared for extreme cold. Cities and municipalities in colder climates have long relied on salt and sand to manage icy roads, but new technologies are improving efficiency. Smart sensors embedded in highways detect ice formation in real time, and meteorological modeling helps optimize road treatments. Meanwhile, some regions are adopting geothermal sidewalks and underground heating systems to keep urban zones functional even in severe winter conditions. Heatwaves. Silent killer heatwaves are prolonged periods of excessively hot weather, often with high humidity, that pose serious health risks. Unlike hurricanes or tornadoes, heatwaves arrive quietly, but their impact can be devastating, especially in urban areas, where the urban heat island effect amplifies temperatures. Concrete, glass, and asphalt absorb heat during the day and release it slowly at night, keeping cities warmer than surrounding rural areas. Globally, heat waves are becoming more frequent, more intense, and longer-lasting due to climate change. In 2023, regions across Europe, the US, and China shattered temperature records, with some places hitting over 45 degrees Celsius, 113 degrees Fahrenheit. Heatwaves now kill more people annually in the US than any other weather event, largely due to heat stroke, dehydration, and exacerbation of pre-existing medical conditions. Low-income populations and the elderly are particularly vulnerable during extreme heat events, often lacking access to air conditioning or adequate cooling centers. Power grids, strained by high demand for cooling, can fail, turning a dangerous situation into a life-threatening one. The 2003 European heatwave claimed over 70,000 lives, underscoring the dire consequences of underestimating this silent killer. Governments are responding with heat action plans, urban greening projects, and reflective roof coatings that help mitigate urban heat. Some cities are planting cool corridors of trees and creating heat refuge centers open during peak hours. Public awareness campaigns now emphasize hydration, avoiding outdoor activity during the hottest times, and checking on vulnerable neighbors, small actions that can save lives. Droughts. The invisible disaster droughts are prolonged periods of below-average rainfall that lead to water shortages, agricultural failure, and ecological stress. Unlike other extreme weather events, droughts develop slowly over weeks or months, making them harder to recognize and respond to in real time. Yet their long-term impacts can be just as catastrophic, crippling economies, displacing communities, and devastating ecosystems. Droughts come in several forms: meteorological, lack of precipitation; agricultural, soil moisture deficits; and hydrological, reduced water in rivers, lakes, and aquifers. Compound droughts, when multiple types occur together, have become more common, especially in regions already stressed by overpopulation and deforestation. The American West, the Horn of Africa, and parts of Australia frequently face these compounded threats. Climate change intensifies drought conditions by increasing evaporation rates and altering precipitation patterns. In many places, rain is not just decreasing, it's becoming more erratic. A region may swing from record dry spells to sudden downpours that provide little long-term relief. This disrupts traditional agriculture cycles and forces many communities to rethink water storage and usage. Innovative drought mitigation strategies are being tested worldwide. Israel, for instance, uses advanced desalination and wastewater recycling. California is expanding aquifer recharge programs and satellite monitoring of soil moisture. Rainwater harvesting, smart irrigation, and drought-resistant crops offer hope. But even the best tech must be coupled with strong policies and international cooperation to secure water for future generations. Hailstorms. Sky-falling ice hailstorms occur when strong updrafts in thunderclouds carry raindrops upward into extremely cold areas of the atmosphere, where they freeze into ice. These frozen droplets can circulate within the storm, accumulating more layers of ice before gravity finally wins and they fall to the ground as hailstones. Some hailstones grow to the size of golf balls, or even softballs, inflicting massive damage to crops, vehicles, roofs, and windows. While hail can occur in many parts of the world, the central United States, particularly Colorado, Nebraska, and Wyoming, experiences some of the most intense hailstorms globally. This area is known as Hail Alley, and it's home to billion-dollar losses annually due to hail damage. In 2010, a hailstorm in Phoenix dropped ice chunks the size of baseballs, causing over $2 billion in insurance claims. Hail forms in environments with strong instability and significant vertical wind shear, which helps lift and sustain the frozen cores within the storm. The longer a hailstone is suspended, the larger it can grow. The largest hailstone ever recorded in the U.S., found in South Dakota in 2010, measured 8 inches in diameter and weighed nearly 2 pounds. This illustrates how violent the forces inside a thunderstorm can become. To mitigate hail damage, researchers are exploring improved forecasting models, radar detection systems that can identify hail-producing storms in advance, and materials designed to better resist hail impact. In agriculture, some farmers use protective netting or even cloud seeding technologies in hail-prone areas, although the effectiveness of the latter remains a topic of debate. For now, quick shelter and preparation remain the best defense. Wildfires and firestorms. Flames out of control. Wildfires are uncontrolled fires that burn in forests, grasslands, and other natural environments. They can be ignited by lightning strikes, human activity, or even power lines. While fire is a natural part of many ecosystems, clearing dead matter and encouraging new growth, today's wildfires are burning larger, hotter, and longer than ever before. Fuel buildup, prolonged drought, and higher temperatures are pushing these fires to catastrophic levels. One of the most extreme forms of wildfire behavior is the firestorm, where intense heat and rising air create powerful winds that fan the flames and make suppression nearly impossible. Firestorms can generate their own weather systems, including pyrocumulus clouds and even fire-induced lightning, which can spark additional fires. The 2018 Camp Fire in California and the 2019-2020 Australian bushfires are examples of fires that exhibited firestorm behavior. Urban wildland interfaces, where cities meet forests or shrublands, are increasingly at risk. As development expands into these areas, the chances of property loss and human casualties increase dramatically. Firefighting resources are often stretched thin, and evacuation windows can shrink from hours to minutes. The smoke from these events also poses severe respiratory risks, often affecting areas hundreds of miles away. New technologies are being deployed to fight wildfires, including drones for aerial mapping, satellite monitoring for early detection, and AI models that predict fire spread based on topography and weather. Prescribed burns, where controlled fires are set to reduce fuel buildup, are gaining acceptance. But experts agree, adaptation and better land management are key to reducing wildfire risk in a warming world. Atmospheric rivers and bomb cyclones. The hidden forces. Atmospheric rivers are long, narrow bands of moisture that flow through the atmosphere, like rivers in the sky, transporting vast amounts of water vapor across continents. When they make landfall, particularly along mountainous coastlines, they can unleash torrential rain and snow. The U.S. West Coast frequently experiences these events, which can bring beneficial water to drought-parched lands or cause devastating floods. These systems are both a blessing and a curse. One strong atmospheric river can carry more water than the Amazon River at its peak. While they help refill reservoirs and snowpacks, they can also cause landslides, flash floods, and infrastructure failures. The 2023 Atmospheric River series that struck California brought both relief and destruction, highlighting the need for precise forecasting and preparation. Another extreme event is the bomb cyclone, a rapidly intensifying low-pressure system where the central pressure drops by at least 24 millibars in 24 hours. These explosive storms can bring hurricane-force winds, blizzards, and storm surges. They often hit coastal regions, particularly the northeastern U.S., where they're sometimes dubbed nor'easters. The term bombogenesis is used to describe their sudden and violent development. Understanding these hidden forces of the atmosphere is critical in a changing climate. Meteorologists are now using advanced computer models and satellite observations to track and analyze these systems in real time. Forecasting their strength, trajectory, and moisture content helps authorities make early decisions on evacuation, flood control, and emergency response. As these events become more common, our ability to anticipate them must evolve just as quickly. Extreme weather is more than just breaking news footage. It is a force of nature that tests the limits of science, engineering, and human resilience. From the chaos of tornadoes and firestorms to the creeping threat of drought and heatwaves, these phenomena represent the edge of our planet's atmospheric behavior. And while they may appear random or uncontrollable, each one follows a set of scientific principles that we are beginning to decode. As we navigate a changing climate, our relationship with extreme weather is also shifting. The lines between natural variability and human impact are blurring, and with them, our ability to rely on historical patterns. Predicting the unpredictable has become a priority for scientists and city planners alike, as preparation becomes the most reliable form of defense. The more we understand, the better we can respond, not just to survive, but to adapt. So next time you hear thunder crack or see satellite images of a swirling superstorm, remember, you're witnessing the Earth in motion, its atmosphere pulsing with energy. Behind every hailstone, lightning bolt, or towering cloud formation lies a story of science, beauty, and power. In learning how to read these signs, we take the first step in mastering the world's wildest forces, and maybe, just maybe, learning to live with them.